Now we know the meaning of resolving power. So in our syllabus, we have to see the expression for the resolving power of the two optical instruments. One is a microscope, which is used to observe very small object like the cell structure, and other one is a telescope, which is used to observe the very huge object in the sky, heavenly body, like this. So first we will see the resolving power of the microscope. Resolving power of microscope. Resolving power of a microscope, like this. So now we know the use of compound microscope. What is the arrangement of the compound microscope? This is the body of the compound microscope. This is the tube attached to it. Like this. Here is a platform where there is a hole, lens. Here is the object, you can say specimen. This is covered with the glass plate, cover slip, and some stainer are used. Stainer liquid. This is the objective lens. This is a eyepiece lens. This is the normal arrangement. So the object is kept here. If we were to illuminate the object, then here on this end there is a concave lens. So light coming from the window is passed through this object. So light. So the object is illuminated like this. So object may be self-luminous or non-self-luminous. दोन प्रकारचे ऑब्जेक्ट असतात. हे जे ऑब्जेक्ट हे नॉन सेल्फ ल्युमिनस ऑब्जेक्ट असतात. सो नाउ दिस लिक्विड has a certain value of refractive index mu. Therefore, the light has wavelength lambda, but when this light passes through the liquid, its wavelength will change. So the wavelength is lambda medium. Lambda minimum obviously less than lambda. So this is the objective lens. So objective lens will produce the diffraction pattern of the two objects which are very close to each other. The distance between the two objects is of the order of micrometer, and therefore it is called as a microscope. The two objects at a separation of micrometer are seen just resolved by using this type of device. It is called as a microscope. So the arrangement is like this. We are using two objects, O1 and O2. So this is the objective lens of a microscope. This is the principal axis passing to the optic center, like this. So this is the objective lens. Objective lens. So one object O1 is kept here. So its image is formed like this. So one ray of light is incident at the upper edge at point E. This point we will denote by A. So it is refracted through the lens, and suppose it meet the axis at point this. Second incident ray is drawn at the lowermost end. This point is B. This point is A. It will also meet at the same point. So I1 is the image of the object O1. Now the another object, I will show I1 here. Another object O2 is kept at a short distance here. They are in the same plane. So distance between the two objects O1 and O2 is denoted by, say, E. So from now we have to form the image of O2. Rule is same. O2 पासून दोन incident ray काढले. One incident ray A ला काढला. तर तो रिफ्रॅक्शन झाल्यानंतर इथे येतो. O1 च्या खाली इथे आपल्याला इमेज मिळेल I1, I2. Another incident ray is drawn here. It will also meet here. So I1 and I2 are the images of the object O1 and O2. The two objects are very close, like this. O1 and O2 are two objects separated by distance A. Then AB is A and B are endpoints of objective lens of a microscope. I1 and I2 are the images of the objects O1 and O2 formed by lens. Lambda is equal to wavelength of light emitted by objects. Wavelength of light in air. Lambda m is equal to wavelength of the light in medium or liquid of a refractive index mu. The mu is equal to lambda upon lambda m. This is equation E. A refractive index is given by this type of relation. I1 and I2. These are the centers of diffraction pattern. Of O1, which is central diffraction pattern of O1, which is central bright disk. I2 is equal to center of the diffraction pattern of O2, which is the central bright disk length. So here the two iris disk patterns are observed like this. So this is say central bright disk of I1. This is central bright disk like this. So these are the iris disk pattern of object O1 of object O2. These are the central bright disk. So Rayleigh's criteria is fulfilled. The first dark ring is coinciding with the central bright disk. The first dark ring of one diffraction pattern is coinciding with central bright disk of the another diffraction pattern. So condition of resolution is satisfied like this. Now here this condition is satisfied like this. So you can show the intensity distribution graph like this. This is the central bright band of I1 and this is the like this. So first minimum of one diffraction pattern is coincided with the center maximum of the another diffraction pattern. So either you can use the Rayleigh's criteria or this is the iris disk pattern. Both conditions can be used for resolution like this. Now this is the ray diagram for the deriving the expression for the resolving power of the microscope like this. So this microscope is used like this. So how this resolution is obtained, that is the rule. According to Rayleigh's criteria, first dark ring, first darkening of I1 should coincide with central bright disk of O2 as shown in figure 1. Therefore, O1 and O2 are just resolved. So this is the condition for just resolution. O1 and O2 are just resolved like this. Now, what to find the formula for the resolving power, and for that purpose, we have to find the part difference either at I1 or at I2 like this. So this alpha is a semi-vertical angle subtended by the object O1 at the lens now. अपन A आणि B हे एक्शन पॉइंट कन्सिडर केलेले आहेत. Also, now this criteria is satisfied. the first dark ring of I1 coincides with the central bright disk of O2, and therefore O1, O2 are just resolved. So what is this limit of resolution A for just resolution condition that we have to find, because this is the two objects which are just resolved. So A is a when O1 and O2 are just resolved, then distance between them, distance E between them is A is equal to linear limit of resolution, linear limit of resolution, and resolving power RP is equal to 1 upon E. 1 upon E. So we have to find the value of E like this. Expression for E. Expression for E. And for that purpose, we will find the part difference. Optical part difference at I1 or the light waves from O2 is part difference is equal to O2 BI1 minus O2 AI1, and therefore part difference is equal to, now O2 BI1 means it is equal to O2 B plus BI1 minus O2 A plus AI1, but due to symmetry फिगर मध्ये बघा, this AI1 is equal to BI1, AI1 BI1 cancel झाले, and therefore part difference is equal to O2B minus O2A. This is equation 1. Also part difference is equal to, part difference जर आपण दोघांमध्ये काढला तर तो O2B minus O1A, so that is equal to this O2B is equal to A sin of alpha, and this is minus A sin of alpha because it is in the fourth quadrant. So this is equal to 2 times A sin of alpha. This is equation 2. So equating 1 and 2. Equating 1 and 2. Part difference is equal to 2 times A sin of alpha. This is equation 3. But for first dark ring of iris pattern, part difference is equal to 1 multiplied by lambda m. This is equation 4. Therefore part difference is equal to 2 times A sin of alpha is equal to lambda m is equal to lambda upon mu. हा फॉर्म्युला आपण यूज करू, लॅम्बडा एम इकडे आणला, म्यू इकडे आणला, आणि therefore A is equal to lambda upon 2 times mu sin of alpha. This is equation 5. where mu times sin of alpha, mu is constant for a given liquid strainer, alpha is constant, mu alpha is equal to constant is equal to Na. It is called as a numerical aperture because it is simply number. Numerical aperture is short form upon Na केलेला आहे, and therefore A is equal to lambda upon 2 times Na. Therefore resolving power of microscope is equal to, put value here, 2 times Na upon lambda. So resolving power is always inversely proportional to the wavelength. Smaller the wavelength, more is the resolving power. तर हाच कंक्लुजन आपण मागे नोट डाऊन केलेला आहे. इलेक्ट्रॉन मायक्रोस्कोप किंवा स्कॅनिंग मशीनसाठी आपण वेवलेंथ पिकोमीटरमध्ये यूज करतो. वेवलेंथ इज व्हेरी स्मॉल in case of scanning machine. Therefore resolving power of the scanner, body scanner machine, CT scan is the highest, then X-ray, then compound microscope, then simple microscope, then naked eye, like this. So RP is inversely proportional to lambda and it is directly proportional to the Na. So resolving power of the microscope is given by this relation. For microscope, like this. The resolving power की definition आपण already बघितलेली आहे. Resolving power is given by this relation. It is a reciprocal of the linear limit of resolution, like this. Now we will consider the special case. So what is the special case? If the objects are self-luminous, like a star, like a slit, then there is a change in the value of the particle. In equation 4, we have to add the Abbe factor like this. When the objects are self-luminous, then part difference is equal to 1.22 lambda m. Equation 4 dash. 1.22 is called Abbe's factor. Abbe is the name of the scientist. Abbe's factor. Therefore, A is equal to 1.22 lambda upon 2 times mu sin alpha is equal to 1.22 lambda upon 2 times Na. This is equation 5 dash, and therefore resolving power of microscope is equal to 1.22 2 times Na upon 1.22 lambda. This is equation capital E. This is equation capital E dash. Theory is है, फक्त a correction factor add हो जाए. There is no 1.22 factor because object is non-self-luminous. So what is the difference between the two cases? Object is non-self-luminous. In this case, the object is self-luminous. So when the object is self-luminous, we have to add the Abbe's factor 1.22, and it is included in the equation of the part difference, like this. So this is the value of the resolving power. Now you can give the definition of resolving power of microscope. His definition is the reciprocal of the linear limit of resolution is called as resolving power of microscope. The reciprocal linear limit of resolution is called resolving power of microscope. Therefore, Rp is equal to 1 upon A. This equation. A is a linear limit of resolution. So this is about the resolving power of the microscope, like this. So now we have to see second instrument, telescope, astronomical telescope particularly, resolving power of telescope. So we know the difference between microscope and telescope. Last year we have seen this. Microscope is used for observing tiny object. Telescope is used for observing very huge object. For microscope, the object distance is very small from the microscope. In this case, object distance is very large. So telescope is used to observe huge bodies like stars, etc. at very long distance away from Earth. Therefore, a resolving power of telescope is inversely proportional to 1 upon angular limit of resolution. Angular limit of resolution. So therefore, Rp is equal to 1 upon theta. Now what is this theta? Here the objects like stars are self-luminous So how this theta is given, that what to see. So these are the two stars S1 and S2. This is the surface of the earth. Earth surface. This is a telescope mounted on the surface of the earth. Telescope. So one ray from S1 passes through the optic center other ray passes through optic center from H2. So this wavelength is lambda. This angle is theta. This angle is also theta. This is A aperture of the telescope, like this. So these two angles are vertically opposite angle. So this distance between the two stars is, say, D or A, and this is capital D. The two sources, the two stars are at distance D. So S1 and S2 are the two stars observed just separated. Therefore, theta is equal to angular limit of resolution. Angular limit of resolution, and theta is equal to this is the distance between the two objects. Theta is equal to d upon d. Equation 1. Also, theta is equal to lambda upon E. This is equation 2. Therefore, equating 1 and 2, theta is equal to lambda upon A is equal to d upon d. D is equal to linear distance. This is equation 3. Linear distance between S1 and S2. Capital D is equal to distance of the two stars. Distance of the two stars from Earth. Lambda is equal to wavelength of the light. Wavelength of the light from the stars. A is equal to aperture, that is diameter of the objective lens in a telescope. For self-luminous object, like star, we have to add the average vector. Theta is equal to 1.22 lambda upon A. 1.22 is the average factor. And therefore, resolving power is equal to 1 upon theta is equal to A upon 1.22 lambda. So this is the formula for resolving power. आपण ॲपर्चरला ए सिम्बॉल यूज केलेला आहे, काही ठिकाणी सिम्बॉल त्याला डी यूज करतात. सिम्बॉल नीट फॉलो करायचे ते. सो दिस इज द एक्सप्रेशन फॉर द resolving power of telescope. Like this. So in this way we can find the expression for the resolving power of telescope and microscope, like this. So for solving the problem, equation 3 is used. Now what is the difference between the ordinary telescope and radio telescope? That is important. Radio telescope, the name itself suggests that radio telescope uses radio waves of longer wavelength, wavelength or resolution instead of light waves. Therefore, since lambda is large for radio waves and resolving power R is equal to A upon 1.22 lambda. Since lambda is large for radio waves and resolving power R is equal to, therefore, to get same resolving power RP, we have to increase the aperture A of the telescope. This is the requirement. So necessary condition is this: to increase the resolving power of the radio telescope, but to increase the diameter, and that diameter is of the order of several kilometers. A should be of size in kilometer. And therefore an array of disc antenna, we are using this type of disc antenna for our TV reception, TV signal. An array of disc antenna is used to increase aperture. In GMRT, giant meter wave radio telescope, giant meter wave radio telescope. The GMRT, giant meter wave radio telescope, is installed in Maharashtra near Pune, near Naranga. So you can see the picture given in our board book. So it uses this small disc antenna, nearly 30 disc antenna of 45 diameter each are used. In GMRT, 25 disc antenna, 30 disc antenna each of diameter 45 meter are spread over nearly 25 kilometer area at Naranga. So this type of GMRT arrangement can be used. It uses the radio waves instead of light waves, therefore it is called as the radio telescope, like this. So this is the main difference between the astronomical telescope and radio telescope. So radio telescope uses the radio waves of longer wavelength. We know the electromagnetic spectrum. Gamma rays are having very short wavelength gamma, then X-rays, ultraviolet, visible, infrared, then radio waves, and lastly there are some waves like this. So this radio wave has very long wavelength. Therefore, if we increase lambda, then we have to increase the aperture to get the same value of theta, to get the same value of resolving power of the telescope. And therefore म्हणजे ऑप्टिकल टेलिस्कोप सारखे जर रिझॉल्विंग पॉवर पाहिजे असेल तर आपल्याला ए इन्क्रीज करावं लागेल. सो लॅम्बडा इज लार्ज, देअरफॉर ए इज ऑफ द ऑर्डर ऑफ किलोमीटर. A should be of the size of kilometer, and this is possible by using this type of arrangement, GMRT, Giant Meter Wave Radio Telescope. It uses 30 disc antenna, each has diameter of 45 meter, and it is spread over the 25 kilometer by 25 kilometer area, like this. So this is the use of radio telescope for getting the radio waves from the distant star, like this.